a polar axis steel shaft parallel with the Earth's axis, supported on its spherical north end by 4 hydrostatic oil pad bearings, a steel yoke bolted to the sphere that holds the gear to rotate the telescope east and west, and the counterweight to balance it and the drives to rotate it north and south. An antenna made up of an aluminum truss superstructure which supports the aluminum solid surface and 4-legged focal feed support. The earliest and longest field assembly was the aluminum superstructure, which was welded piece by piece upside down at the site. The first large sub-assembly to be fitted to the assembled superstructure truss work is the declination gear girder with counterweight box section. This 20-ton aluminum fabrication was lifted with ease by one of 2 large guy derricks, each capable of lifting 250 tons. Each hoist load line has 32 parts. Control is precise in good hands. The girder holds the bronze declination gear and 36 tons of concrete and steel counterweighting. Proper construction scheduling would place installation of this gear girder after the declination shaft was in, but this and other components were delayed in shop fabrication. So the job worked with the pieces which were at hand, with no reliable delivery dates for those still missing. Finally, the declination shaft came up the road. This 68-foot shop fabrication had been built once before, shipped to the site, rejected as inadequate, trucked away, fabricated again, damaged in the shop, repaired, hastily shipped by rail again, and offloaded just 1 day ahead of the July 1964 threatened rail strike. Had the shaft been further delayed, the job would have had to shut down. On hand at last, it was snaked under the erected gear girder and fitted into place. The declination shaft is one of the most complex sub-assemblies in the telescope. Its aluminum shell is adjustable about a steel central shaft. The quill assembly allows the antenna system to be precisely adjusted to the true declination axis. The steel shaft is adjustable so as to bring the declination axis precisely perpendicular to the polar axis. With the declination shaft in place, the fit-up of braces, beams, gussets, and stiffeners began. All members of the superstructure will produce a stiff, highly compliant system in which the paraboloidal surface has no deflection in winds of up to 15 miles per hour and takes no permanent set in winds up to 135 miles per hour. This weldment is made of the heaviest known aluminum rolled sections. To our knowledge, the overall tolerance of plus or minus 1/8 of an inch on such a large structure has not previously been attempted or accomplished by welding aluminum in the field. We were fortunate that highly skilled craftsmen and very delicate construction equipment were available to build this component. Special techniques of field welding were developed for heavy aluminum sections, and a specialized group of welders was trained and qualified on the job. The aluminum is 54-56, the wire filler being deposited in a helium-argon mixture. All welds were die-checked. Strength welds were radiographed. Now the 180-ton weldment must be raised to add to its diameter and depth, and it must be moved out from under the derricks whose heft was needed on other heavy assemblies. The lift involved a calculated overload on both derricks. The lift was started, then stopped to weigh it with hydraulic jacks. Calculated weights had been correct. The derricks were lifting 20% over their rating. They rested with the load. Nothing gave, so the lift resumed. It was followed up with piles of cribbing blocks, insurance for a while, then continued to the proper elevation without backup blocking. 2 steel A-frames mounted on railway trucks to form a single carriage were rolled underneath it. The structure was lowered until the declination bearings were secured to the A-frame tops. It was then towed by a truck 60 feet out of the way. In the new location, cantilevered aluminum trusses to hold the outside surface panels were tied in. The outermost stringers were fitted to the cantilevers, checked for position and elevation, and final welding began. Meanwhile, other parts began to arrive by rail from the fabricators' shops. The hub of the yoke was among the first. This piece, which bolts to the north end of the polar shaft, required a special railroad car to bring it from East Pittsburgh to the siding at Bartow, West Virginia. It was desirable that the yoke hub weldment be fabricated in as large a piece as possible and under controlled shop conditions in order that this 137-ton nickel steel casting, welded to 6-inch plate, could be heat-treated, radiographed, and then precision machined to fit the sphere. A selected crew accompanied the move for a period of 2 weeks, breaking apart the car, lowering and raising the weldment as necessary to clear tunnels. The car permits its load to be suspended between 2 identical end sections which can be pulled apart. Over the road, the load is part of the railroad car, and for tight spots, it is lowered to the minimum possible track clearance. The size of the weldment was dictated by the availability of this car and by clearances which its use would allow in passing through the mountains. The tightest fit encountered was a natural rock tunnel at Droop Mountain. A bend in the tunnel brought this piece less than 3 inches from the rough rock tunnel roof and sides, and by this much the load passed through. A trucker's lowboy took the piece from the side track at Bartow over the 11 miles to the construction site. Calculations indicated that existing bridges on that route would not support loads such as this one, and it was obvious that the uneven road surfaces often would not allow sufficient clearance under the lowboy. All 7 bridges between the railroad siding and the construction site were shored to take the weight. Mats were constructed and placed to distribute the load on bridges and to smooth out rough spots in the road. Mats were set ahead of the move, picked up and reset for each weak, soft, high, or rough spot en route. While the principal problem in transporting this piece for the railroad was size, the problem for the trucker was weight as well. This fabrication was not the heaviest transported, but it was the most cumbersome, concentrated weight moved over the winding roads. There were predictions that tires would blow out, wheels would buckle, and the load would overturn. These predictions were real. This piece is slightly under 200 tons on a 75-ton lowboy. Along with a dozen other sections that make up the yoke, the hub weldment made it to the site. Each section was fitted into its proper position next to the pedestal in the spot under the derricks where the superstructure had been. The yoke is an all-welded A201 steel structure involving many plates up to 6 inches in thickness. Completed, the assembled yoke itself weighs nearly 600 tons. In addition, The cylindrical bottom half will hold 700 tons of heavy density concrete for rough balance, plus about 35 tons of cast iron trimming blocks for fine balance about the polar axis. All pieces were welded into the largest sub-assemblies which the derricks could lift. Constant checking, controlled welding sequences, preheating, careful welding supervision, and 100% radiographic inspection were applied. Then the polar shaft arrived, almost a year late and in the middle of the winter. It too came by rail to Bartow and was offloaded and chalked on the same lowboy. This time we have 210 tons of weight on the 75-ton trailer. This shaft is a combination of A201 steel plate up to 6 inches thick, welded to two 3.5% nickel steel castings. It is finish machined to tolerances within 10,000ths of an inch. While it was not the most concentrated weight, it is a very costly piece and a most cumbersome component to handle. It was brought to the site with 2 tractors pulling and 1 pushing. Here it waited for receipt of the sphere, which was still being machined at the fabricator's shop. The 17.5-foot diameter nickel steel sphere being machined at Westinghouse is the pivot for telescope support and rotation. It is machined from a single casting and is certainly the largest ever poured in 3.5% nickel steel. Unusual tooling was required to machine the sphere to a tolerance of 3/1000ths in both sphericity and circumference. It has a plate glass finish of between 10 and 20 micro-inches. At last, the sphere has arrived at Bartow. A special single casting railroad car was built to transport this 160-ton piece. Very special handling devices and very careful rigging are now essential to remove it from the car, rotate it 90 degrees, and land it upside down without damage. Where? On the same lowboy. The value of the sphere, FOB Bartow, West Virginia, is about $1 million. It is the heart of the telescope and is now the keystone to all subsequent construction. This time, luck is getting thin with this remarkable piece of trucking equipment. As it starts onto the shored and matted bridge at Bartow, it sticks fast. The concentrated weight has so bellied down the trailer that there is too little road clearance despite the matting. The lowboy supporting the sphere was jacked up and additional runners placed. A second truck again attempted to push from behind, but it too was crippled by the resistance of the heavy load. Damage to date? 2 broken tractor axles and 1 front end. Quite a crowd for the third try, which now adds a mobile crane to act as a winch. Teamwork is essential in this operation. Grease plates are added on top of the mats to lessen the resistance of the mass and provide a ship launchway surface to slide on. After being bogged down for 5 hours, the signal was given to try again. This time, success. It goes across and starts up the first hill, now with 2 pullers, 1 pusher, and the truck crane winching from the top. A welcome sight on Route 28. After so many years of delay, everyone takes notice. Contemplating another delay at an expected trouble spot, the load surprisingly makes the turn with ease. By now, all components are on site. The panels for the solid surface have begun to arrive and are stored. Behind them, the focal feed support is being welded together. Well back, the superstructure is still being welded together. Closer at hand, the yoke has been fitted up and sub-assemblies are being welded. The shaft is now ready to receive the sphere. For the first time, the two will be joined together. The 28 studs which hold it to the shaft were first threaded into the sphere. Coated with asphalt paint and covered with fiberglass and resin to protect its machined surface, the sphere engaged the 10-foot diameter spigot of the shaft. A risky business. It is a tribute to the construction contractor that the sphere was so rigged for the lift to fit it on the shaft that it hung plumb. Hanging so, the sphere with its 28 500-pound studs was drifted without interference onto the shaft. This operation was accomplished without any damage to the stud threads, which were protected by lengths of stovepipe. The sphere now joined, its stud nuts were run up inside the shaft, and each was tensioned to 950,000 pounds by means of a power-driven wrench procured just for this job. It is now possible to start erecting the telescope. The assembled shaft and sphere are the first to be rigged to go in the air. A problem with lifting the sphere and shaft into place was to locate the pick points so that at the final rest angle of 38 degrees and 27 minutes, neither derrick would be overloaded. The weight of the unit is 386 tons. Its center of gravity was located and the pick points were set so that at none of the lift angles to follow would either derrick be overloaded. No miscalculations allowable here. Some doubted the calculations. The shaft was tilted to the required angle. Telephone control was established at each winch house in order to be sure that one derrick did not get ahead of the other. Clearance between the derricks was not enough to pass the load straight through, and so it was angled between the two booms. Once clear, the shaft was cautiously drifted south, the worst point for this 2-derrick lift. The gallery increased in numbers as the lift started down to enter the tail-bearing housing and to land the sphere on the jack and hydropads. Here, it is in unstable equilibrium and twice slips south. It must be blocked until the yoke weight can be added. Mechanical components have meanwhile been under construction on and inside the pedestal. Each of 4 main supporting hydropads and each of 4 cylindrical positioning hydropads in the tail bearing will receive about 11 gallons per minute of hydraulic fluid. The telescope thus floats and is held in position by a 5/1000 inch film of oil. The flow to each hydropad recess is constant and is maintained by 32 constant volume, constant speed pumps, delivering oil at pressures up to 4,500 pounds per square inch as called for by each pad recess. These pumps are located on the second floor of the foundation. The operating console and workspace are located on the main floor. The telescope will be controlled electrically from this point. In this submarine-like passageway on the third floor, auxiliary hydraulic and electric equipment necessary to float, rotate, and brake the instrument is located. The piping is not the least complex part of the work. Outside again, the second major lift has begun. Sightings of Polaris have shown the polar shaft to be correctly aligned with the Earth's axis, so further erection proceeds. This was the first of the 4 sub-assemblies which in the air will become the yoke. The first to go up is the centerpiece which will fit on the sphere. Other sub-assemblies have been moved back and the center, with hub, is raised off the ground. Here again, the angle of the piece is all important. It must hang so that the hub is at the angle of the sphere to which it will bolt in the same way that the sphere bolted to the shaft. Every man on the site was involved, one way or another. The yoke center is the heaviest lift made. A single pick point was used with a balance beam to equalize the 460-ton load between the derricks. Thus, neither hoist was overloaded, but position control could be only by tag lines. Again, the piece will not pass between the derrick booms and must be angled through. Now on the north-south center line, the hub must be drifted south and lowered at the same time. Coordination of the separate derricks to do this is essential. The first points of contact are 4 tapered dowels engaging the hub bolt holes to index the piece while lowering. The dowels enter, so the indexing is satisfactory and lowering continues. But the face-to-face angle, so carefully planned, is off by several degrees. It is decided to risk hanging up on the 10-foot diameter entering spigot. The male and female are size for size. Lowering continues, and it hangs up about half entered. The next day, a rigging truck tied to a live oak tree pulls south, 100-ton jacks push north, the derricks heave, and the hub goes home. This weight will now stabilize the shaft against further slips to the south. The next and second yoke piece is the bottom counterweight section, which went on as soon as the hub was bolted to the sphere. Again, the trick is to pick up the 110-ton bottom section at the correct angle so that it will butt up exactly with the center yoke assembly. This is the section of the yoke assembly which will receive 700 tons of concrete counterweight and steel ballast. The lift turned out to be one of the easiest. The match between the 2 sections was good, and the section previously pre-fitted on the ground was quickly clipped and tacked in place. With the erection of the yoke counterweight section, it is possible to make up some of the time lost by late delivery of fabricated components. Around-the-clock shifts are set up. High above the ground, welding has to be completed before counterweighting and further erection can continue. Excellent progress is made. During this time, yoke alignment checks were made and preparations for counterweighting went ahead on the ground. High-density ilmenite ore was washed, graded, and weighed. Using a portable crane, the ore is hand-placed inside the counterweight sections of the shaft and yoke. About 40% of the laid-up volume was in voids left by this iron ore. The dry aggregate was pumped full of ferrophosphorus mortar, finally to yield a concrete with a density of 250 pounds per cubic foot. Almost 850 tons of this concrete were so placed. With bottom-heavy balance established, the next step is to erect the yoke arms. Both will be erected together, suspended by a balance beam made up of a huge tank 67 feet long and 17 feet in diameter. Both derricks are necessary in this 200-ton lift, which again must be twisted to pass the derrick booms. No other location for these derricks is possible because of the superstructure lift to come, so there are difficulties with the preceding erection. The lift continues. The lift is stopped. There is trouble. The north hoist is too blocked. The pick points are too high. Swing the derricks. Drift the load. Bump the south boom. It doesn't buckle. And enough height is gained to set both arms, as per plan, 19 degrees south of plumb. The arms are clipped, tacked, aligned to the polar axis, and the high welding begins again. The yoke is completely assembled. Machinists drill to dowel the bearing shims in place. Now power is brought to the temporary turning gear on the polar shaft. A gear reducer is installed. The load tank is filled with 66,000 gallons of water. The hydraulic system is started up and the system is rotated for the first time. Does it turn concentric with the polar axis? No. It is adjusted at the tail bearing. Is there too much torque about the polar axis? No. The balance calculations were correct. So rotation continues. First hard west, next hard east. It is a working machine, but it bounces. The assembly has a natural frequency of 2.1 cycles per second, and the hydraulic system forces oscillations of up to 5/8 of an inch vertically about the polar axis. The vibration is controlled by reducing the oil film thickness most of the time. Observatory personnel take over rotation. The contractor begins installation of the permanent polar drive gear around the counterweight section of the yoke. The gear girder plates are welded in place and torch cut to the proper radius as the structure is rotated about its polar axis. Separate gear segments are hung to this girder plate. The added weight reduces the vibration by stiffening up the spring. The critical task is to align the segments to make a satisfactory single gear out of 28 pieces. Despite expansion and contraction from daily temperature variations and periodic vertical oscillation, tolerances of 2.5 thousandths of an inch are maintained. Reference was made to a master block each time a new segment was being set and checked by pin indicators. Once checked, drilling and welding, reaming and driving of bolts were all part of the operations necessary to set and hold alignment. A total indicator runout of plus or minus 20 thousandths of an inch was achieved. These horseshoe-type hydraulic spring brakes are the largest ever known to have been fabricated. When set on the polar gear, the three apply a total braking force of 630,000 pounds. The design is fail-safe, and if a power failure occurs, the brakes will automatically lock on the gear sides. The problem now is to install, align, and test the reduction units and the 50 horsepower hydraulic drive package. The polar gear is red-leaded to show tooth contact. The brakes are released with observatory operators at the power package on the main deck, at brake stations 1 floor below, in the pump room on the 2nd floor, and at the main console down on the ground floor. Communication is established and the first test of the structure in rotation under its power begins, and is successful. The bouncing has gone. The mechanism will be stable. With the tests complete, the structure is rotated hard to the east and held there with temporary kicker beams which brace it from the main deck. A complete unbalance will be set up when the load tank comes off. The tank is drained and it is easily cut loose from the yoke arm on the bottom. It hangs up on the bolts to the upper west yoke arm. The 2 derricks finally pull the top loose without damaging the hold-down bolts, and the load begins to be lowered out of the way. This test tank, filled with water, simulates the superstructure weight while setting the polar gear and testing the brakes and drives. The superstructure could not be used for these tests because it will not swing past the 2 derricks, which could not be otherwise located, and lift the superstructure to its final position. Every erection step has been planned around these 2 derricks in their location, dictated by the superstructure lift. The aluminum superstructure is now completely welded and has been moved within reach of the 2 hoists. Steel pick points have been built into it for its lift. Pickup location is of prime importance to divide the load between the derricks. A calculated unbalance has directed their placement in the structure. The falls are shackled to the load. The winch truck is rigged to hold back, and this 210-ton structure is lifted 2 feet free of its support cribbing. It is stopped to be weighed for unbalanced force. Close enough, says the rigger, and signals the lift to begin. The trick is to raise and rotate simultaneously so that the declination bearings will land on the yoke arm ends. Years of model practicing by many people have preceded this erection. Some have declared the maneuver impossible. Some have quit to avoid being identified with the attempt. Word is out. The gallery comes to see who wins. The 20-degree point, then a 30-degree angle is reached. The parking lot fills to capacity. "45 degrees, and the complexity of this truss work is really observable for the first time. At 50 degrees, there is a snap at the south pick point. At 55 degrees, the north pick point shifts 2 inches. The structure shudders, but everything holds. By 75 degrees, the tension is considerable. A tape recorder and 2 cameras are covering the job now. The holdback crane begins to flash and sound the overload warning bell. The failure comes quickly. The lift swings down 4 feet and the bottom corner has dug in. A 1 3/8-inch holdback cable to the truck crane has parted. But the derricks hold. The main load lines hold, and the welding holds. There is no damage except to the cable. The load is secured to the pedestal and control of its imbalance is established with 2 observatory vehicles. The gallery goes home, as do we all. The next day, the superstructure is lowered to the ground. The south pick point had allowed too much imbalance for control of the lift. This connection is raised to bring the superstructure center of gravity further east of the load lines. Hold-back control is positive by tying off the bottom to the pedestal. The lift signal starts it up again for the second try. Initial liftoff is much easier. Adequate control has been provided. All the contractor's top offices are present. The rotation upward goes as planned. Nothing groans or gives. The movable holdbacks have adequate control. The structure is pinwheeled to align its bearings directly with the yoke arm tops when it was found to be some 10 degrees off center. The lift went successfully, almost to the planned position. Then, clearance ran out between the superstructure and the south derrick. More clearance was provided by cutting away some of the lifting device. The booms were at the limit of their topping, but the bearings were in position to start entering their keys into the keyways on the yoke arm tops. Almost an entire second day was required to make the fits, engage the temporary turning gear with its pinion, enter the bolts into the declination bearing housings, and sledge up the hold-down nuts, which finally secured the superstructure in place. Because of limited and awkward working space, these operations continued to be directed from the ground. Now the 2 derricks can come down and the 60 surface panels can go up. They are rigged on the ground to the proper, predetermined angle and plane, then lifted, one at a time, to be held at 4 support points on simple jack screws. These jacks, engaged in clearance holes, provide the adjustment by which each panel will be brought to its exact position in the paraboloidal surface of the antenna. These antenna sub-assemblies were shop fabricated to give a solid aluminum surface tolerance not in excess of 30,000ths of an inch, root means square. Panels are installed from the bottom up in order that all control can be from above. The work goes on except when winds prevent it. Edge clearances between panel sides and ends are maintained at each layup. Only by so doing was it certain that there would be room for the panels to follow. Each of these assemblies was trucked over 750 miles from the fabricator's shop. Some were bumped, bent and strained in transit and during handling on site. But instrument checks demonstrate that they have satisfactory compliance. Each element can take over 1/2 inch of differential deflection among its 4 supports and will return to its paraboloidal shape. No deflections are expected in excess of 3/8 of an inch in winds up to 135 miles per hour. After final adjustment of the panels in place, they will be painted white with a heat-diffusing coating material. They are not painted prior to erection so as not to lose the 90 reference marks by which their shape can be measured. While the panels go up in the foreground, behind this activity, the derricks have come down. These landmarks will be missed after 6 years on the local scene. As soon as enough surface is on to expose the mounting holes, the 4-legged feed support is erected. This 65-foot structure has been completely welded on the ground and will bolt to the superstructure through the panel apertures provided. It is swung up and into place by one truck crane carrying 190 feet of boom and jib, assisted by a second truck crane and the ground crew on tag lines. The donut-shaped top is built to support 1,000 pounds of receiving equipment mounted on an adjustable feed support. The truss-stiffened legs will prevent its deflecting more than 3/8 of an inch from wind or gravity under normal observing conditions. The vertical axis of this support, in line with an instrument support stand above the apex of the paraboloid, determines the focal axis of the antenna. All components are adjustable to assure the correct location of this axis with respect to the surface. After the feed support and instrument stand are in place, the last panels are installed. Both derricks have been taken down and mothballed on site. The third winter of this construction period is well advanced, but the work goes forward with Christmas Day as the target date to be finished with all erection. The last panel is approached with some concern. Will it fit as a proper shutter plate, or have the calculations and measurements been off? One shingle on this surface will mean fitting it all over again. It slips into place with clearance all around. Erection is completed. Under its own power, the telescope starts into zenith position. Once there, the declination drives, brakes, and controls are installed, and the construction job is finished.
Are you getting a TV picture now, Houston? Neil, yes, we are getting a TV picture. You're in our field of view now. That's one small step for man, one giant leap